Okay, welcome to the second day of the mini course. I will give it right away the word to Jamie, please.
Okay, well, thank you very much. It's good to see you all again. Okay, we're talking about how to use neural networks to solve PDEs. And one of the very first things that I said is that when you're doing this process, I mean, there's all different types of variations, methods that people use, but ultimately there's almost always the same 3 steps. And the first step is that you have to define your architecture because we're trying to approximate functions. These may be operators, they may be the solution itself, but we're trying to approximate a function. So we have some parameterization, which happens to be a neural network in these contexts. And then we have to think about how we initialize this and so on and so forth. Later, we define some kind of loss function and we do some kind of categorization of the solution that we want via some kind of optimization principle. Okay, the most typical one being that we want the solution of our problem or the solution of our PDE in the simplest case to be the minimizer of some loss. And in fact, we want to go a little bit further and say if we're near the minimum of our loss, then we have a good solution in whichever metric interests us. Well, later on, the final step is that we actually have to do the optimization itself. Okay, now one thing to keep in mind is that these problems are generally horrifically non-convex. The simplest way to see this is if we just think of a single layer neural network. So we have an affine map from, let's say, 1D. We go to some high dimensional space via an affine map. We apply an activation function, then we apply another affine map to get us back down to R. Okay, so one-dimensional output. Now, if we permute the entries of the layer in the middle, then we get exactly the same neural network, right? All we've done is relabeled the coordinates, but given an input, the output is going to be the same. So this means that we have an amount of symmetry of the order of the number of permutations we have of the nodes, right? This is combinatoric growth. So this tells us immediately if we have a minimizer and we have a huge number of neurons, then we have a huge number of neurons factorial of minimizers. Okay, so this is really, really non-convex. So most of the optimization strategies, I mean, the standard black box ones that people use, I mean, these are just based on gradient descent in one way or another, because we can't say much more about the structure. Oh, the pointer is not pointing. Okay, there we go. So before thinking about the kind of gradient descent that we can use in a numerical discretization, let's just think for a second about what gradient descent does if we have a continuum problem. Okay, so the idea is we have some vector, let's say. We have some function which goes from this vector space to R, and we want to minimize it. And the simplest approach is just a classical gradient descent. We just try to solve the ODE that the derivative of our vector in time is equal to minus the gradient of the thing that we want to minimize. Of course, we have some initial condition. This will correspond to the initialization of our neural network. And you can just apply the chain rule. And what you see is that if you have a solution to this equation, you take the derivative of your loss function and you get something which is negative norm of the gradient of the loss squared. Okay, so okay, this is good because it means that our loss is going down, right? But of course, when we don't just want the thing to decrease, we want it to decrease quickly. And okay, just to do a very, very simple quantitative analysis, if we have that our loss function is just some kind of quadratic function like this, we have a positive definite symmetric matrix A, and our loss is just half A theta dot theta. This is a vector. Well, our global minimum is theta equal to 0, and the ODE is very simple, right? It's just a linear system. And what we have is that the convergence is essentially dominated by the smallest eigenvalue of this matrix. If this matrix has a very, very small eigenvalue, we're going to go very, very slowly. Okay, so a degeneracy in this A is going to lead to slow convergence in the continuum. But of course, okay, we're not solving ODEs when we do gradient descent. We're doing a time stepping type procedure. And of course, this adds extra problems into the mix. So instead of having a continuous time system, we're updating our weights by the previous value minus some number, which is typically called the learning rate, times the gradient. Okay, so again, now if we think of a quadratic loss, the same loss that we had before, just half a theta dot theta. Well, what is the recurrence relationship that we have for theta? Well, now it's of this form, okay? So theta k plus 1 can be written as the identity minus this number times the matrix A applied to the previous value. You can solve this equation basically explicitly as well, just like how we can almost explicitly solve the ODE. What we have is that our theta k is going to be this matrix that we have here to the power of k times the initial condition. So what we have is that the norm of our solution, recalling that our exact, the norm of our iterate, recalling that the exact solution, the exact minimizer is 0. Well, this is going to behave like the norm of 1 minus the learning rate times the matrix to the power of k, okay, where this norm is taken in operator norm. So now what we have are two problems. I mean, in the continuum, we had all of the convergence was controlled by the smallest eigenvalue of this matrix. Once we start bringing in time stepping, then the largest eigenvalue also starts to play a role as well, okay? If we have a gamma such that the 1 minus gamma times the largest eigenvalue of this matrix is greater than 1, here we have exponential growth, right? We're not even going to converge to anything, not even slowly. Everything's going to blow up. And again, this sort of thing can happen if we have that 1 minus gamma times the largest eigenvalue is near -1, then we have a similar situation, okay? So once we go to the discrete regime, we also have a kind of upper bound of what our learning rate can be. And again, if our learning rate is too small, then this is going to be very close to the identity and we're going to converge very slowly. So somehow there's an optimum learning rate where at one end we explode, at the other end we just don't do anything. And so we can see, okay, this is just in a really, really simple toy model. What I've done is I've taken this matrix A to be some matrix where I've taken its eigenvalues to be log uniformly distributed between 0.1 and 10. So 0.2 is this sort of limiting learning rate where things start to explode, so I don't think about what happens here. And we just want to have a quick little look at this plot. Okay, so most of the plots that I've shown, these have been on log scales. Here, my number of iterations, this isn't logarithmic, right? This is a linear scale. So within 2,000 iterations, I mean, we can get down to sort of 10 to the minus 11 in error if we choose things correctly. And as what we see here is that as our learning rate is getting bigger, we're getting better up until this value of 0.199, which is very close to the maximum permitted learning rate. And then in that case, we see this kind of non-linear behavior where it starts off being better and then it starts picking up this issue where we have the eigenvalue very close to the limiting value and it starts going slower, okay? So, okay, this is a very, very toy model, but this is kind of to emphasize the U-shape type behavior where if it's too small, you converge too slowly. If it's too big, you either converge slowly or explode. Now, why did I choose this kind of distribution? One thing that it is known is that if you have some loss function based on neural networks, it is very, very typical to have an ill-conditioned problem, okay? What do I mean by that? The second derivative, which is morally this matrix A, is going to have a horrific condition number, okay? So that's why I've chosen this particular distribution, because we expect in reality that the Hessian matrix that corresponds to our loss function is going to have a really, really high condition number, and this will make training difficult. But there's a further complication on top of all of this. Okay, when we're doing these kinds of problems, I mean, we have some loss function, which is normally defined in the continuum. We say that our loss function is the L2 norm of the strong form residual or something similar. But I mean, one of the things I emphasized yesterday is that integration is a problem. We can't integrate exactly for many, many, many problems. What does this mean? That we're also going to have some kind of error. Okay? And this is why we think of this as stochastic gradient descent. In the world of data science, this is a slightly different beast. But in the world of PDEs, what we can think of is that we have some kind of stochastic error when we're evaluating all of our integrals and the derivative of the loss itself, which correspond to integration errors when using a stochastic integration rule. When we're in some kind of data science-y application and we're thinking of having a finite data set, and what people often do is they divide their data set into batches and they do the optimization over the batches. So what we can think of is that we have some data, which I'm calling HeI, some abstract data that could be basically anything. And we have some kind of stochastic loss function based on samples of the data, and our true loss is an average over this data set somehow, okay? And in our world, if we're thinking about stochastic integration rules, if we're thinking of Monte Carlo integration, then we have an infinite data set, essentially, because we can do as many samples as we like at effectively zero cost. So in our case, we're going to be thinking that we have a kind of stochastic loss function, which is what we can actually access. We can't access the real loss. It depends on some data, which we can think of as our Monte Carlo sample. And we expect, or hope at least, that the expected value of this stochastic loss is going to give us the real loss. Okay. Now, in this case, oh, 1 second, I think I've got the wrong version of the slides up. Which one was it? No, this was this one, right? There's an error that I know I changed. Yeah, this is the correct version of the slides. Okay. So yeah, this was the issue. So we're thinking of this like regular L as being the stochastic loss. This is what we can actually access that depends on the data. Then we have this curly L, which is somehow the true loss. So we think of L theta xi being the evaluation of our loss based on a Monte Carlo sample. And the curly L, this will be something like the L2 norm of the residual that we can't actually touch apart from via the expected value. So in this case, now what we do exactly the same process. We do a gradient update, but now because we can't access the full loss, we use the derivative of this stochastic loss, which gives us a stochastic gradient. So we do the same kind of process. We take theta k plus 1. This is going to be equal to the previous value minus some learning rate times the derivative of the stochastic loss, which is now a stochastic vector. Okay, we have noise in this derivative, which is inherited from the noise in the evaluation of the loss. Now, if we have a sufficiently regular loss function, then okay, if we take the derivative here, we can take it outside the expected value. And then in this case, we can decompose this guy, our stochastic gradient, into the exact gradient plus some error, which if we're lucky, will have mean 0. Yep. Now, this makes training much more complicated. So I mean, this does have some kind of advantages in here. Okay, by having some kind of noise, this can help overfitting. In our case, where we have infinite data, we don't really expect overfitting to happen. But another benefit of this is by having something a little bit noisy, if we have a local minima which isn't particularly stable, it's easier to jump out of it. Okay? If you think of a pure continuum gradient descent, if you're very close to a poor local minimum, then you'll go straight towards it and be stuck there forever. If you have some noise, maybe you can jump out of the well and go into a better local minimum. Okay, so it's not all bad. But this does really impede convergence, and the more noise you have, the worse this is going to be. So, I mean, often the best that we can hope for is to reach some kind of equilibrium steady state solution where we're near a reasonable minimizer, but there's some kind of fluctuation happening around this, right? Now, okay, this isn't really particularly relevant at the level of PDEs type applications, but if you're using something with data, then by doing things by batch, I mean, this adds an overhead cost, even though it can improve convergence, because you update at every single batch, not at every, not globally, should we say. So, okay, this is the same problem as we had before. I'm going to this really simple toy problem. All I want to do is minimize a loss, which is half a theta dot theta. But now I'm just going to introduce some fake noise into my optimization. Okay, so I take exactly the same A as I had before. And now this is a toy model for my stochastic gradient. So it's the exact gradient plus some mean zero noise, which I take to be random uniform with mean zero and variance like 10 to the minus 2. Now, this time we are on a log-log scale. Okay, in the previous results that I showed, this was over 2,000 iterations on a linear scale. Now we're going up to 20,000 iterations and seeing how learning rates affect things. So again, we still have this really, really slow convergence if the learning rate is too small. But when the learning rate is at its largest value, which I take to be 0.1, okay, things seem to be going nicely, and now we're in a pure noise regime. Okay, we're basically not improving at all because this noise is going to be bigger than the updates that we really want to do. Okay, and just to comment on the scale, in the previous experiment, when we got in 2,000 iterations, errors of the order of 10 to the minus 11. This time, we're at 10 to the minus 1. Right, so this really, really does impede convergence. But the other thing that I really want to draw your attention to, if we compare the learning rate 0.1 with 0.01, okay, in this first regime where things are quite slow, things are quite smooth, we have that the bigger learning rate is better. But then once we're in the noise regime, the error is higher than the noise regime when we're in the smaller learning rate situation. So this trade-off between big or small learning rates gets much more complicated when we have noise, because what we can see from here, I mean, this learning rate doesn't just multiply the part which is correct, it also multiplies the noise. Okay? So this changes the kind of steady states that you expect to get. Now, in this kind of toy problem, if we just have some kind of linear gradient and some mean zero noise, then there are some results. Okay, you can basically write by hand what the long-term behavior of this system is. So what you have is that your iterates are going to behave like a normal distribution with mean zero. So zero is my minimizer in this case. Okay, if your minimizer was some other vector, then it would be this one, with some covariance matrix. And the covariance matrix, okay, semi-explicit, it solves a Lyapunov equation. So again, gamma is our learning rate, V is this unknown variance which appears in the distribution of our iterates, and sigma that appears here, this is the covariance matrix which corresponds to the noise. Okay, so we can see that the learning rate is appearing both here and here. And as well, what we can see, okay, you can almost explicitly write the solution to this equation. And the solution, this covariance that appears here, is sort of the order of the learning rate itself. So what this is telling you is that when we're near once we've reached this kind of steady state regime, what we should be thinking of doing is reducing our learning rate so that we reduce this noise. So, okay, decaying the learning rate, this is something very, very common, but as well, it's something very delicate. Okay, so the idea is now we take this number to be something which depends on the iterate that we're in. Okay, you can either do this by prescribing it from the start, you can try to do this in an informed way based on what's happening during your optimization loop, but the idea is that you want it to go down. Now, if you open TensorFlow, PyTorch, whatever, lots of them have built-in functions that do exponential decays of the learning rate when, for example, your loss isn't improving, right? And typical schedulers, so if you decide by hand, I want my learning rate to decay in this form, people tend to go for exponential decay. But I mean, whilst this is common, there's various works which say that the correct option is to take an algebraic decay. Okay, so when you're near a good minimum, you should be taking your learning rates to behave like k to some power, where the power is greater than a half and up to 1. Now, what's essentially the argument here? If you do an exponentially decaying learning rate, then essentially you're not updating enough, right? I mean, you're going too slow, so you don't actually reach the minimum. If you decay not slow enough, too slow, then the noise is going to continue dominating. And the theoretical works say that this is really the correct scaling to ensure both that the noise goes to 0 and you reach the minimizer, okay? So in these regimes, okay, there's a bunch of technical hypotheses, and most of them, I mean, it's true that they don't hold for neural networks. I've said probably, but some of them, they do not hold for neural networks. under a bunch of technical hypotheses with these kinds of scalings, there are a bunch of different results in different situations that tell you that the scaling that you have is that your iterate minus the critical point or minima to which you are converging have this kind of statistical behavior. So essentially the error divided by this learning rate converges to a normal distribution with mean zero and some variance. And the thing to have in mind, if these learning rates are tending to zero, well, this means that something over zero is converging to something order one. So morally, what we have is that the convergence is of the order of the learning rate. Okay, so if we have that our learning rate is like 1 over k, we expect the error to be like 1 over k. Now, again, there's an explicit representation for what this covariance matrix looks like, and it's of this form. This is a different type of Lyapunov equation, but it's a Lyapunov equation nonetheless. And what we have is that, so V, if this is the variance that appears in this limit here, HL theta star, this is the Hessian matrix of our loss at the critical point to which we're converging. And again, variance gradient, this is the variance of the stochastic gradient at the critical point. Okay? Now, you can study this equation and think, okay, qualitatively, what do the solutions do depending on this Hessian, which is given by your architecture and your loss, and the gradient, which is given by your architecture and loss. And essentially, there's two problems. Okay? It should be kind of clear that if we scale this variance by a factor, then our solution V is going to scale by the same factor. So the bigger the variance, the bigger the variance here, the bigger this V matrix is going to be, and the bigger our error is going to be. Okay, so this is kind of obvious. Lots of noise means more error in our solutions. The other property that you can take out of this equation is that if this Hessian matrix is ill-conditioned, then this V is also going to be big. Okay, when I say ill-conditioned, I mean having eigenvalues very, very close to zero. And this is a problem because this is true. Okay, you can evaluate or at least estimate the Hessian in lots of situations. And what you'll find is that you have a few very, very dominant eigenvalues and loads which are sort of machine zero. Okay. So this gives us a big limiting factor when we're converging, even when using these correct scalings of the learning rates. So just to show you in an empirical way what's happening, when we go back to exactly the same toy model that we had before, okay, we're thinking of an exact gradient, which is based on an ill-conditioned Hessian matrix with some mean zero noise. But now I'm going to take my learning rate to depend on the iteration number. So I consider three regimes. Okay, the first regime is the constant regime, which is this blue guy here. So I have, okay, this is the iteration. This is the learning rate for each of the three experiments. The second regime is the exponential decay. So this orange guy, which goes, it's constant up to a certain point and then starts going down exponentially. And then the third is the algebraic regime. So after a certain point, this green curve, this now follows a 1 over k kind of scaling. And you can see the difference when we look at the error across iterations when we use these regimes. Okay, so the blue curve, this is the constant learning rate case. This is more or less what we saw before. Okay, we have some sort of nice smooth decay, and then we just have noise and the game's over. Now, if we use the exponential decay, which is the one that you'll often see if you play around in the literature, we see the kind of behavior that I was talking about before. Okay, at the start, before whilst things the noise isn't dominating, things are smooth. Then we get noisy, then we're starting to improve, but then you can see this little foot here. Now, what's happened here is that our learning rate is now so small that it's not making any meaningful change to our weights. Okay? So it's not that we've converged to the minimum, it's that we're just not doing anything when we're doing our optimization loop. Now, with the algebraic case, so this is this theoretically correct scaling, then, okay, what we have, again, the same smooth regime before noise dominates. Noise starts to play a role. Now we start reducing our learning rate. And this is kind of linear on a log-log scale, which is the kind of behavior that I said before. I mean, if the error is basically the learning rate, okay? Like to be more precise, it's the square root of the learning rate. Okay, the big thing I want to kind of highlight here is if you have some simple deterministic problem, then you expect exponential convergence and you're probably going to get very good solutions very quickly. I mean, noise makes everything really, really different. And the ill conditioning of these problems also make things very, very slow. Okay? If you decay the learning rate, then okay, maybe you can guarantee convergence in some theoretical limit, but this is still really slow. Like 1 over k convergence is incredibly slow. So these processes can take a very long time. And before talking about anything new, are there any questions or comments? Okay. Now, in reality, I mean, okay, gradient descent is much easier to understand, but people don't tend to use that much just a regular gradient descent. What they tend to use are methods based on momentum. So if we go back thinking, okay, where did SGD come from? Okay, we're thinking of just a simple gradient descent. Theta prime is equal to minus gradient R loss. And the idea of momentum methods is that we consider a kind of approximation of a second order system. Okay. So we have some other parameter mu, which appears here. And the way that these tend to be implemented, so okay, this m, this is our momentum vector, which is going to be the same size and shape as the thing that we want to minimize. And we update this momentum vector. By now we have the same kind of minus learning rate gradient, but it also has something inherited from its previous value. Then we update the weights according to the momentum. Okay, this is essentially just a simple discretization of this kind of ODE. It's typically taken close to 1, but okay, in practice, things can change depending on the kind of problem that you have. So a couple of things I want to highlight about this momentum vector. So one thing to have in mind is that this acts as a kind of average of the recent gradients. Okay, if we go back to the expression for the momentum, and the momentum is almost decoupled from theta if we think of it as the gradient as being a separate object. And again, you can write a kind of closed form solution of what the momentum is at a given iteration in terms of the previous gradients, and it's essentially a weighted average. Now, why can this be good? If we're very near a minimum, the gradients shouldn't be changing too much, but they're noisy. Okay, so the exact gradient isn't changing much, but the noise is changing every iteration. You take an average and you hope that the noise diminishes. Okay, so in that sense, it can be useful when you have noisy problems because it does a kind of averaging procedure which diminishes the noise as far as the update is concerned. Yeah, it's something you have to choose. I mean, okay, the way that people update is by this, and then this is the parameter that you normally specify in the program. Okay. This can also be helpful if you have a very flat loss landscape. Okay, because okay, you just think, okay, we have momentum. If I have a ball rolling down a very flat hill, it's still going to pick up momentum and go faster and faster. So this can be useful if we have flat loss landscapes, which is kind of related to this problem of ill conditioning. I mean, ill conditioning is like having a flat loss landscape, more or less, so it can be helpful in these kinds of situations. But as well, these methods, they tend to be a little bit more oscillatory. Okay, in SGD, you tend to expect things to be a little bit more smooth, at least before getting to the noise regime, but these methods can be a little bit noisier. And as well, because it's got this kind of memory effect, where the momentum vector is essentially an accumulated gradient or weighted average of previous gradients, if things are changing a lot, then you're remembering useless information. Okay, so this can also introduce other problems. So now in this case, I'm going back to our really simple 1D pin problem. So we just have U prime prime is equal to F. And I'm taking the learning rate to be the same. And all I'm going to do is vary the momentum parameter. Okay, so this is just SGD with momentum, which is precisely this update rule. And the momentum parameter is this beta that we have here. And we can see quite a significant difference depending on the momentum parameter. Okay, so here we have the loss, again, log-log scale. Here we have the error, log-log scale. And by having a very large momentum in this problem, okay, I'm not claiming that it's going to work in this style for every single problem, but in this particular problem, we see that the use of momentum really accelerates the convergence. Okay, in this regime, I mean, we're much noisier when we have lots of momentum, which is similar to the comment that I just made before. But what we have is that it's getting to a much, much better value at the end of training here. Okay, so we get huge gains. And adding momentum, at least in TensorFlow, this is not even a one-line change of code. You just put momentum equals 0.9 or something like that in a regular SGD optimizer. Now, in general, if we're talking about some kind of nonlinear optimization program or non-convex optimization program, you might want to try and go for some kind of Newton method. Okay, these tend to be very, very fast when they work, at least. So the idea is we can approximate our loss function as some constant plus something linear plus something quadratic, and then we can minimize this quadratic form exactly just by doing a bit of linear algebra. If we can access the Hessian and we can access the gradient, then what the Newton method says is that the optimal update should be of this form. So this tells us a few little things. I mean, one of the things is that we should be thinking that this Hessian is morally like parameter-dependent learning rates. And different parameters are doing different things. Why should we be using the same learning rate for every single parameter? If we just think of some simple one-layer network, why should we be doing the same optimization procedure or using the same parameters for our optimization procedure for the weights and the biases? Because they have different roles, so maybe you should be doing different things. And in principle, the Hessian should be able to capture this kind of behavior. Of course, in neural network type applications, this is not at all feasible for various reasons. And the main one is cost. Okay? If we have orders of thousands of variables, which is typical, then we're talking about order of thousands of derivatives that we have to find in order to evaluate the Hessian matrix. I mean, even storing this thing can be a problem, let alone evaluating it. And the other thing is, just like with the gradient, I mean, we usually can't access the exact gradient. We can only do some kind of an approximation via quadrature. Now, if we have a horrifically ill-conditioned matrix here, and now we add integration errors, then this system is going to be horrifically ill-conditioned. Okay? So even if we were willing to put the time in to try and evaluate the Hessian matrix, these errors are going to lead to a really, really unstable update scheme here. But nonetheless, what this is telling us is that we should be thinking, what can we be doing differently to the different kinds of parameters that we have within our network? Now, the Adam optimizer, this is the one that you will probably see most of the time if you start looking through literature based on neural networks and PDEs. Again, in all of the typical packages, this exists as a black box. And essentially, it's kind of like a momentum and kind of optimizer. Okay, I won't go into the details of exactly what it does, but the idea is that you have this momentum vector, which isn't too different from the one that we had in SGD with momentum. It's morally a weighted average of previous gradients. But then there's another vector, which is an estimation of a weighted average of the gradient squared. Okay, when I say squared, I mean component-wise. So our gradient is going to be however many trainable variables we have. We just do it component-wise to get a vector of the same size. Okay, so as you're doing your optimization loop, you update your estimates for the averages of these quantities, so the gradient squared and the gradient itself. And then the update step that you do, okay, there's update steps for this MK and VK, which I won't write down. But the update is theta k minus some fixed number times 1 over the square root of this VK. You normally put a little regularization constant here to make sure you're not dividing by 0 at any point, times the momentum vector. So this is very, very hand-wavy, but you can kind of argue that this vector VK is somehow trying to capture the most important features, both of the Hessian and of the noise, and integrates them into your optimization in such a way that you try to compensate, right? Okay, this is not a rigorous statement at all. This is complete hand waving, but it tends to work really well. Okay. So this is normally much, much, much faster to converge. Okay, I use it, I think, almost 100% of the time, I think. And one thing that I think is a really, really useful property of this optimizer is that it's quite resistant to the initial learning rate. So if we just quickly go back to, where's SGD? SGD here, okay? Now, if I multiply my loss by 10 to get the same behavior in an optimization loop, I need to divide my learning rate by 10. Okay, so there's somehow a problem with scale here. You need to know an intrinsic scale to your problem to be able to choose the learning rate. But Adam is quite a bit more resistant to this, because if we look at this property here, right, this VK, which is an effective estimate of this quantity, its square root is of the order of the gradient of the loss itself. The momentum vector is of the order of the loss itself. So if I multiply my loss by 100, then it doesn't really change that much the rest of the optimization loop. So this makes it kind of resistant to scaling to some extent. Okay? And this is something that I find quite a lot. I mean, generally with Adam, if I'll only ever try sort of learning rates, this gamma, which you still have to specify between 10 to the minus 2 and 10 to the minus 4. With SGD, maybe I need to try over many more orders of magnitude to get something that actually doesn't blow up or actually moves, right? One thing to note, I mean, there's all kinds of parameters that sit inside the Adam optimizer. So, okay, when we had the momentum-based update, we had this beta parameter, which was used to update the MK. There's another parameter which is used to update the VK. There's this regularization parameter. I mean, there's all kinds of things that go into it that really need to be tuned, but the off-the-shelf ones, most of the time seem to do okay. Okay, so let's just do a quick comparison of SGD Adam and SGD with momentum. So I'm taking the same PIM problem that I had before. And what we can see, okay, so this, which one do we have here? So blue, this is just a regular SGD. And what we can see is that it appears to just get stuck and do absolutely nothing. And at the start, okay, there's a different behavior here. What we have is that the momentum guy is starting off better, but then again, it gets stuck and goes off into a plateau. Whereas the Adam one, okay, it ends up with a better performance at the end, even though it's not doing quite as well at the start, okay? But one thing to keep in mind, I chose the parameters for SGD and SGDM with momentum based on trying various ones and seeing which one worked best. With Adam, I just did the default ones, right? I mean, I just didn't specify anything. If I'd have spent more time playing around with all of these different hyperparameters in Adam, I could probably get something better, okay? So this is what I mean by saying it's quite resistant to the choice of parameters. So I mean, when you're implementing these things, I mean, there's basically zero difference in cost between using momentum or Adam, right? I mean, these are kind of order epsilon changes to the code in comparison to evaluating the loss and evaluating its derivative. Okay, so you don't lose anything by trying these guys. I mean, there's no extra cost really, but they can really, really help the speed of convergence. And Adam really is the optimizer of choice that you tend to see more than any other one. And other thing that I mentioned before, I mean, you have different parameters which sit inside your neural network with different roles. So it may be that we should be thinking about different approaches depending on the role that these parameters have inside your neural network. Okay, so Adam tries to mimic this in the simplest way possible, but this is a kind of underlying principle which I think is quite important, right? Okay, the simplest case is just using different learning rates depending on which bit of your network you're dealing with. So, I mean, of course, there's other strategies that can be done when you're doing an optimization. And one that I want to put a bit of emphasis on, which really emphasizes this idea that you have different parameters that do different things in your network, is what's being called like a least squares solver. Okay, so remember when we were thinking about Newton methods, we had this horrifically ill-conditioned matrix. We can only evaluate it by quadrature, which means that we introduce errors. It's huge as well. It's of the order of the number of parameters that we have. So this isn't really feasible at all. However, if we have a fully connected feed-forward neural network, so just classical neural network, nothing special about it, we can write our neural network in this form. So if we think of the UNX as the outputs of the one but last layer, right? So we have however many nodes that we have. These all get multiplied by some trainable parameter, and this is what gives us the output, right? We have a kind of dot product between some vector of functions and some vector of trainable parameters. We can understand this as a basis of functions produced by our neural network and some coefficients that we want to try and identify, okay? We're really thinking the parameters that appear in the last layer of our neural network, we can understand these in a very different way to the parameters that are in the rest of our neural network, because these act like coefficients on basis functions in the same way that we would understand this in linear algebra, okay? Now, even though our loss function in the parameters is typically horrifically non-convex, what we have is that in terms of the neural network itself, rather than the parameters, we often apply loss functions, which are quadratic, right? Something like the L2 norm. The deep Ritz method is based on a quadratic functional, even though it's not a norm. And in these cases, if we have our network decomposed in this form, so Cn are some of our trainable parameters that have very special roles, we can take our loss function. This is just thinking, just to make things concrete, about a simple interpolation problem. Well, our loss function is just the sum of the errors. These are our inputs, these are our outputs squared. Okay, this is the thing we want to minimize. By putting in this representation of our neural network into here, well, we just do a few simple algebra calculations. And what we end up with, okay, obviously this is going to give us some kind of quadratic loss in these coefficients, okay? We can explicitly write what this matrix here is, right? This depends on both n and m, the indices of each of the coefficients. This gives us a quadratic term, this gives us a linear term, and there's a constant, which we don't really care about if we're minimizing things, right? Now, what is the idea here? If we think of these guys, these basis functions, as being fixed, this is now a lot easier to solve. I mean, this is a kind of much better, well-posed minimization problem than this horrifically convex guy that we started with. So the idea is that if we split our trainable parameters into two classes, the linear parameters in the sense that the output of our neural network is linear in the parameters, and then the non-linear parameters, which are typically the ones in the earlier layers, we can think of our loss function as some matrix, which depends on, I'm calling omega, the non-linear parameters. Okay, so these are all of the ones apart from the ones I called C. This gives us a matrix, which in principle we can evaluate. Then we have our linear parameters, dot linear parameters, the same with a vector, which depends on the non-linear parameters, dot product with this vector. Okay? And again, a constant term that I don't care about because I'm minimizing. Now, if we can calculate these guys, then viewing these parameters omega as fixed, then it's really simple to find the optimum C, the optimum coefficients, okay? So almost what we're doing here is we're thinking of the neural network as producing a basis. We try to find the optimal solution over a basis. And now by substituting this solution into our loss function again, we can try to optimize over the rest of the parameters. And this is now a horrifically nonlinear problem, so we have to do something like SGD, Adam, etc., etc. Okay. So the article of Sear, which is the same one about this initialization that I spoke about yesterday, they call this an adaptive basis viewpoint. So what we're thinking of is that the neural network is producing a basis, and then over this basis, we can use what's essentially classical techniques. Right? I mean, we can think of this almost as being like a finite element method or similar. Okay? There's a whole world about these kinds of methods, which you tend to call subspace methods in other contexts, which is the same idea. We view the neural network as producing a function space, and then over this function space, we do classical or almost classical techniques then we train the neural network to make the solution using classical techniques the best one possible. Okay? So I'm only really going to talk about the case in the really, really simplest problems here, where we just want to solve some linear PDE. But this is the idea. Okay, so we do linear algebra effectively to find the coefficients. Then we train the basis functions with SGD, Adam, whatever, because it's horrifically nonlinear. So this method, this can be very, very good at approximating oscillatory solutions. This can be very good at converging quickly. And in many cases, it may be that gradient methods can get trapped in much more easily in local minima. This tends to be a little bit more resistant. But there's still this problem of ill conditioning. Okay, it's not as bad as you would expect in the case where we have the sort of full problem with an ill-conditioned Hessian, because these coefficients come from a positive definite symmetric problem. Okay, so at the very least, we shouldn't expect negative eigenvalues appearing in the matrix that we have here. But nonetheless, these basis functions may be very, very ill-conditioned with respect to the problem that we have. I mean, they may be very close to linearly independent, and this happens with standard initializations. I mean, if I take these Gloret initializations with a hyperbolic tangent activation function, it's very likely that after the first iteration, everything's going to explode. Right? Why? Because this matrix is horrifically unconditioned. We evaluate this inverse. Our coefficients are nowhere near what they should be, and we end up with poor solutions, and this is horribly unstable. Okay? So I mean, a good initialization helps a lot when you have these kinds of problems because of this conditioning issue, to which it is very sensitive because of this inverse. And as well, this also means that it's much more sensitive to integration issues. Even if you have a good basis, good I won't define, then it still won't be a very well-conditioned system. Okay, so it's still going to be sensitive to integration errors, which can introduce instabilities. But even though I'm going to be talking about the particular application, I mean, the key idea I really, really want to emphasize by talking about this is that you have different things in your network with different roles, and we should be thinking about different ways to optimize over them given this. Just to show you an example of the difference that you have here. Okay, so in this case, I've taken the deep Ritz method. So the deep Ritz method, this was this version we saw before, where you have the integral of the gradient squared plus f times u. Again, this is a quadratic loss in our neural network, not in the parameters, but in the neural network. So we can apply this idea. If we think of the coefficients as being something that depends on a basis generated by the rest of the neural network, we can do a linear algebra step to find the coefficients, then optimize the loss over the basis functions in this sense. So what I have here is a very oscillatory solution. Okay, this is my exact solution in dotted red, which maybe you can't see at the back. Now, the least squares solution is the green one, and you probably can't see any difference between the green line and the dotted red one, which is on top of it. Okay, you get a very, very good solution. But what happens when you use Adam is that you have this dotted blue line, and it seems to be picking up these really, really, or the higher amplitude bits of the oscillation. But here it just kind of gets stuck in something flat because it's not capable of capturing the high oscillation components that we have here. Okay? Now, if we look at how the loss behaves, okay, we can see it here. Okay, we have Adam, which is, both of them are kind of flat at the start, but this is something you always see when you're training a neural network. This is because of the ill conditioning of the problem. Then it starts to improve, but then Adam essentially gets stuck. And you can almost see why it's getting stuck here. I mean, it needs to simultaneously go up and down, right? I mean, to approximate these kinds of oscillations. And there's just too much symmetry, essentially, so that these forces, if you want to think of it in that way, cancel out, and it just gets stuck as some kind of average, right? It's just not really doing anything. But our least squares guy is able to overcome this, and we get very, very close to the value of the exact loss. Okay, so remember in the deep Ritz method, the minimum of our loss is some negative number, and it's not equal to 0, so this isn't log-log, right? I mean, it's like minus 600 and something. Okay. With the error, what we can see if we look at the H1 norm, how this converges over our iterations, we see a much more extreme version of this on a log-log scale. I mean, you can see exactly how Adam is getting stuck at a really high error, whereas the least squares guy goes boom, 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 and now we're basically stuck in the noise regime, which is to be expected. We're always going to end up in a noisy regime. Now, this issue with having problems approximating the oscillatory types of solution, I mean, this is very well known. This is called spectral bias. In some contexts, it's called the F principle, F meaning frequency. And essentially, what it says in a non-rigorous way is that if you want to approximate a function with a neural network, then it will generally do a very good job at approximating the low frequency components, and then it struggles to approximate the high frequency components. And this is something which is very well known, and you can see it perfectly in this situation. So this kind of method, I mean, it does some work at the very least to overcome this F principle. But as well, and something to keep in mind is if you're expecting very, very high frequency solutions, I mean, these are the situations where you should be thinking also about the architecture. So what I said yesterday about these sirens initializations, which are kind of morally a Fourier transform and then something nonlinear afterwards, and these can be much more useful for overcoming this problem, which you see all the time. Now, just to highlight what I said about that these things can be very, very unstable. When I did this simulation, I used a really, really fine integration mesh, which is basically, I mean, it's not feasible once we're talking about 3D problems. Right? This is a 1D problem, so essentially you can put tens of thousands of points and integrate up to numerical zero, right? Now, if I use fewer integration points, I think it was of the order of 50 or 100 or something like this. I mean, now we see that the least square solution is awful. Right? I mean, what we have is that our loss is, okay, the exact loss is this red line. Somehow we're going to minus 500,000, which, okay, if we're lower than the exact minimum, this is telling us there's some really significant integration errors which are going on. And if we look at the errors that are produced by this during the training, okay, we can see it starts to go down and now it's just going crazy and blowing up. And we've got something which is useless, essentially, okay? So whilst this is a very, very attractive method, it does come with a lot of questions about scalability. Okay? So all of this I've said. Okay, so one last thing that I want to talk about. So this is one method that was proposed for trying to overcome the spectral bias problem. Are multi-level neural networks. Okay, so this is one particular work where I mean, there's various people that have tried to do similar things, but I'm going to be using the idea of one particular piece of work. This is kind of based on the idea of refinement, if you think of classical methods. So if we have some very, very simple linear PDE, what we can think of is we do some training, we have some solution, the solution isn't going to be perfect, there's going to be some error. Now, this error, according to the F principle, is probably going to have higher frequency components than the ones that are approximated by the solution that we've obtained before. So what we can do is define the error. So U0 is the solution that I obtained after my first training. Now I think, okay, U1, this is my error. My error also satisfies a PDE, right? Okay, in this case, an ODE. This is because it's linear. So if I now fix my U0, okay, my F is known. Obviously, this comes from my PDE. Now I can train a different neural network, keeping this one fixed, and try to minimize the error. Okay, and then we can try and reclaim a better approximation by doing, well, U0 plus U1 should be a better approximation to U. So we can do this iteratively over and over and over again and try to get better and better and better solutions. Now, because of this F principle, what we expect is that the U1 will have high frequency modes, then the solution in the next step will have even higher frequency modes, and so on and so forth. So what they proposed in their work, which is kind of morally equivalent to the idea of this sirens initialization that I mentioned before, is they took that once you go to the next layer, the next iteration, the next refinement, what they do is instead of thinking of their input of their neural network as X, they think of it as some vector of X. cosine some number times x, sine some number times x, so on and so forth, right? You know that you have high frequency components in your solution, so you put them into the input of your neural network so that it's able to approximate the high frequency components of the solution. Okay? Really, the main difference between this and the sirens initialization is that in the sirens initialization, these guys would be trainable variables. What these guys did was put the numbers in themselves. Okay, so they say, okay, in the first refinement, we'll use k going from 1 to 10 or something like that. In the next, we'll go from 10 to 20 and so on and so forth. But morally, it's basically the same idea. Whereas in a sirens initialization, you would just take the sampling from which you take these weights to be bigger and let them train during the process. Now, this idea appears a lot in other contexts, right? So you have some fixed numbers and you put high frequency components into your neural network. These are normally called Fourier features, and people tend to do this when they expect oscillatory solutions to make it easier for the neural network to approximate these oscillatory solutions. So here I did a little implementation of their method. And so these dotted red lines, these correspond to the points where I did the refinement. So what you can see, so this is our first stage of training. Things are flat because they're always flat at the very, very start. Then you start to get an improvement. Now we're in the noise regime. So I say, okay, I'm going to stop training this guy because it's not gaining anything at all. Now I freeze the guy that I had before, and now I add a second neural network on top, which is now the one that I'm training. Continue the same process. Now we're in the noise regime and so on and so forth, right? So I do this, 4 times. Now, what we can see, you can see very, very clearly how this F principle is working, right? At the end of my first refinement, this is what my error looks like, right? I mean, this is about as low frequency as you can be when you've got 0, boundary conditions. Then once we look at the error after the second refinement, so now this is the sum of U0 and U1 minus the exact solution. Okay, now we start to see more oscillations appearing. But another thing to keep in mind is the scale. Here, my biggest value is 0.08. Here, it's 0.0005. At the second refinement, now we're at 10 to the minus 5 orders of magnitude. We're starting to see very, very oscillatory behavior here. And at the end of training, now we're of the order of 10 to the minus 6. And all we have are really high frequency components to our error. Okay? So just to do a comparison, one could ask, okay, at the end, essentially, we just have a sum of 4 neural networks. And what we've done is we've trained one, then we train the next one based on the first one, and so on and so forth. Why not just train them all together? Well, okay, let's do that. And then what you see is that the error that we have, okay, whilst it's lower than the error at the end of the first refinement, it's still got this property that all we see is a very, very low frequency error. And we can check by looking at the orders of magnitude here. I mean, this one gets down, and it's about an order of magnitude higher at the end of training than the other one in H1. So this second bit on the optimization strategy that I wanted to say is, I mean, going beyond just simple gradient-based strategies where we say, okay, we have a horrifically nonlinear problem. I'll update my weights according to the gradient. If we go beyond that and think in different ways about how we can optimize our neural network, then this can make things much more accurate. There is this issue of spectral bias, which is behind us, and we should always be thinking, if I'm expecting oscillatory solutions, how can I make my network approximate them well? And as well, we have an optimization issue there, that our errors are typically going to be in the high frequency regime. I am personally a very, very big fan of these least squares based solvers. But they come with their problems. I mean, if we're in more data science type approaches, it's not clear at all how this should work when you have batches, right? Because if you have this matrix, which is unstable, and you now evaluate it by batches, I mean, this is very, very complicated to work out how to put together. It's very sensitive to errors, which also brings in another problem. Once you're in a 3-dimensional problem, there's a big question of how do you integrate to get the linear algebra system you want to solve to reasonable accuracy. And as well, it's got the limitation that somehow you need the loss. Sorry, this should be quadratic in the NN. Okay, if you have something which is truly nonlinear, then there's a much bigger problem there. And yeah, so this part I've already said, but I'll repeat. So yeah, I mean, iterative strategy, you can use the F principle to try and use an iterative process to try and get the higher order frequencies at different parts within your training. Okay. Yeah, it's up to you to choose, and you have to hope that you've chosen well. Yes, I mean, and that's why I said the Fourier features approach. I mean, this is very common, I mean, not just in the PDEs community, you see it in other works as well. But my personal opinion is that if you're doing something like this, I mean, okay, you wouldn't put, especially once you go to higher dimensions, I mean, the number of frequencies somehow scales with your dimension exponentially. You have a curse of dimensionality. So if I want to put all of the frequencies between 1 and 4, but now I'm in 3 dimensions, I have 111, 112, and the number blows up. So you have to put a huge amount of information in it. I mean, my personal opinion is that the better thing to do would be to use the sirens initialization, initialize these frequencies to something which is a lucky guess, let's just hope, and then let it train to adapt to choose the right frequencies at the end of training. Right? And I think that's all I wanted to say on in this session on optimization. And so please ask if you have more questions.
Yeah. Question? You can bring up the question to the comment page, which is on the bottom. So let's thank Jenny for the moment. Yes. So the main network for the country, since I can look the north here and